Hi, I'm Norman Wahlberger. Today we're going to look at the full group of Euclidean isometries, including not just reflections and rotations that we've already been discussing, but also translations. And along the way, we're going to look at an alternate way of thinking about reflections and rotations through the idea of the half slope. So let me remind you of this very familiar situation, I hope. We have a point on the unit circle, and we can rationally parameterize that point by its half slope h. Here's h, point on the y-axis. We join it with this point here. We get this point E of h, which has this explicit familiar rational parameterization. The point A, we might also refer to its x and y coordinates as AB, as we have been previously. So let's now exploit the fact that we have two ways of thinking about the point A, both as the point AB in terms of x and y coordinates and as given by this half slope. That motivates us to introduce some slightly new notation. So the reflection sigma AB, which we've already talked about as being sigma A, so these are just the same things. We're going to now introduce a third notation for it, just sigma sub h, because h is the half slope of A and h determines the point A. So we can represent this reflection not just by the point A on the unit circle, but also by the number h, which is the half slope of that point A. And exactly in a similar fashion with the rotations, we have rho AB, otherwise known as rho sub A. We can now refer to that also as rho sub h. Now, in terms of the geometry of things, I remind you that this line here, which determines the point E of h, if we translate it down to go through the origin, then it will still have slope h. Slope here is h over 1. And so over here, if we draw a line tangent to the unit circle at the point 1, then that height being h, then this line will also go through there. And this line here bisects the separation here. In other words, the reflection through this line is exactly the reflection sigma h that we've been talking about, that sends the identity element to the point A. So remember, we specified a reflection in terms of where the identity element, or the point 1, is sent to when we reflect. Okay? So if 1 is sent to there, then it's that point which specifies the reflection. And now we're seeing that this half slope h, which figures in this notation, exactly describes this, this line here, which is actually the axis of the reflection. It's a line with slope h going through the origin. So this is a very attractive and important picture. I hope that in years to come, undergraduates will just be very, very familiar with the geometry here, purely in terms of rational materials, no angles involved, no sines or cosines or tans. Okay, it's just all a rational story. Works even over a finite field, exactly the same story. So now we're in a position to restate the fundamental formulas that tell us how to compose reflections and rotations in terms of their half slopes. And the key for doing that is this theorem here, which we've already talked about, that if we're just talking about complex number multiplication on the circle, so I remind you that we have the circle, points on the circle can be multiplied. And in terms of the half slopes, here is the formula that expresses the multiplication, that E of h times E of k is E of h plus k over 1 minus hk. Great, so now we can rewrite the formulas for the multiplication or composition of grounded isometries. The reflection sigma h followed by the reflection sigma k, so these are the half slopes of these reflections, will be the rotation given by this half slope, k minus h over 1 plus hk. Rho h followed by rho k is rho of h plus k over 1 minus hk. Sigma h followed by rho sub k is sigma h plus k over 1 minus hk, the same one here. And rho sub h sigma sub k is sigma k minus h over 1 plus hk, the same thing that figures here. So as a little exercise, you can check these formulas. These are just ways of rewriting what we already know. And I remind you, a little bit of a hint is that if A is E of h, then its conjugate A bar, which figures in the way we presented these formulas previously, is E of minus h. That's giving you the reflection in the x-axis. If that's a slope of h, then that's a slope of minus h. So we can work with the algebra of reflections and rotations purely at the level of half slopes, and that's often a very powerful thing to be able to do. One important application of that technology is to study powers of reflections and rotations. The reflections are easy. If you take sigma sub h followed by sigma sub h according to the formula, that's rho of h minus h over 1 plus h squared. But that's just rho of 0, which is the identity matrix, telling us something that we already know, that if you have a reflection and you do it twice, then you get back to where you started. In other words, that's the identity transformation. So powers of reflections are easy. Powers of rotations are considerably more subtle. And we've talked about this already when we were talking about duplicating sectors to see how many of a particular sector fits inside some larger, say, unit turn. But let's now look at things algebraically with the aid of these formulas that we have that tell us exactly how to multiply rotations using their half slopes. So if we have a rotation of the half slope h and we take its nth power, we could perhaps write that just like that without the brackets, then we want to get some kind of hold on that. And to do that, let's introduce this circle sum. So this is just the expression that appears in our formula for multiplication of points. So h sub 1 circle sum h sub 2 is by definition h1 plus h2 over 1 minus h1 h2. So then we can express the product of two rotations, rho sub h followed by rho sub k, to be rho of h circle k instead of h plus k over 1 minus hk. So just a little bit of notation. The circle sum then is another number. You have two numbers, h1 and h2, rational numbers for us typically, and then the circle sum will be another one. But we have to keep in mind the possibility that when we're parameterizing the circle, there's really also an extra parameter, the parameter infinity, which is floating around, which represents the point on the far left of the circle, the minus 1, 0. Okay, so if you get a denominator here of 0, well, that's telling you that you should interpret that to be the point infinity. In other words, you're talking about the point minus 1, 0. Half slope of infinity corresponds to the point minus 1, 0. Okay, so let's see if we can exploit this to understand powers of a rotation. Now, there's some pleasant algebra here, which I'm going to leave to you as some nice exercises. So the first one, exercise 92.2, is to show that this circle sum, which we've so far defined for two things, has the following form when we extend it to three things. So if we take h1 circle sum h2 circle sum h3, we get this number. Have a look at this. h1 plus h2 plus h3 minus the product, h1, h2, h3, divided by 1 minus, and then this sum h1, h2 plus h2, h3 plus h1, h3. So I hope you recognize the four symmetric functions of h1, h2, and h3. That's the constant symmetric function. That's the linear symmetric function. That's the quadratic one. And that's the cubic one. Okay, and so now we can ask the question, what happens if you have a rotation of half slope h and you repeat it? You do that rotation and then again, and then again, and then again, and again. Where are you going to end up after you do it a certain number of times? So we can do this algebraically now in terms of half slopes. And what it really amounts to is just calculating the circle sum of a particular h with itself several times. So, for example, h circle sum h. Show that that's equal to 2h over 1 minus h squared. And then when you go to 3 of them, you get 3h minus h cubed over 1 minus 3h squared. So these two are just special cases of the ones we've already got. And then to go one further, if we have 4 of them, we get 4h minus 4h cubed over 1 minus 6h squared plus h to the 4th. And then to stare at these things and ask yourself, how's this going to generalize? And can we prove what the general case is? So the hint is to look at the whole thing. Don't just look at the numerator and the denominator separately, but try to look at the whole expression. You should see something very familiar in all of these. It's quite a pleasant story here. And it also reiterates our understanding that working with rotations is intrinsically hard. The half slopes are getting more and more complicated as you just perform these doublings, triplings, quadruplings, and so on. At the level of angles, you don't understand this. This is hidden to us because we're just pretending that we have angles, and then the angles just double or multiply by 3 or multiply by 4. But in fact, we don't actually really have angles exactly. So that's all just a pretend or approximate technology with angles. Here we're insisting on knowing exactly what we're talking about, and we necessarily have to deal with complexity. There's complexity in this story when you repeat a rotation many times. And the greater the power that you take, the more complicated this thing gets, and there's just nothing you can do about it. It's just the way it is. Great. So we've understood grounded isometries pretty well now. Let's move to the more general situation of trying to understand general isometries of the plane. So we have an object in the plane, and we're willing to rotate it, we're willing to reflect it, maybe reflect it again, and we're willing to translate it. And we're willing to rotate it about some other points and reflect it about other lines. Okay, so we can have this thing end up in quite arbitrary positions. And so we want to understand these general isometries that take the plane and send it to itself in such a way that all the metrical structure that we're used to is preserved. In other words, the quadrants between points and the spread between lines is preserved. So it turns out that what we have to do in addition to the reflections and rotations is not all that much. We have to introduce translations. And that's relatively easy because translations are really just determined by vectors in a very simple way. So let's remind you of a particular notation that I like. So if v is the vector rs and a is the point AB, then let's define a plus v to be the point a plus r, b plus s. So we think of a as being an absolute position. We think of v as being a relative position. It's a relative quantity. If we take an absolute quantity and we add a relative quantity, we should get another absolute quantity. So this is another point. And we'll say that a plus v is the translate of the point A by v, because we've moved it in the direction of v. And we're going to introduce a new terminology for that, sort of like the rotations and reflection terminology. So we'll write a plus v as a followed by tau sub v. Well, that's just our notation. Tau sub v is a symbol that we use when we put it to the right of a point. What that means is this. It means that we're taking the point A and we're adding the vector to it. So here's the point A, and here is a tau sub v, where that's the vector v, same as that vector there. There's the origin. There's the origin O, followed by tau sub v. There's the point B. There's B, followed by tau sub v. Now in this case, we're used to these symbols also being interpretable as 2 by 2 matrices. We're not going to be able to do that here for translations. So just note that in this case, this is not to be interpreted as a 2 by 2 matrix. It's just a symbol at this stage, which we agree combines with a point to give this translated point. And there's some relatively elementary and simple arithmetic with translations. If we have tau sub v followed by tau sub w, so the composition, then that's the same as tau sub w followed by tau sub v. So this is commutative. And in both cases, we get tau sub v plus w. That's illustrated in this diagram here. So here's a point A, there's a vector v, there's a vector w. So if we translate A by v, we get this point here. This is A tau sub v. And then if we translate this point by w, we get A tau sub v followed by tau sub w. And we know geometrically that translating here and then translating here is the same as simply translating by the single vector v plus w. So this can also be written as A tau sub v plus w. So that's the reason for this. Tau sub the zero vector is the identity. If the vector that you translate by is nothing, then you're staying where you are. And that actually is the identity, which is can be interpreted as the usual identity matrix, if you like. But it's just the identity translation. And inverses, well, if we want to invert translating by v, we should translate by minus v. That will send us back to where we came from. So here's a point B. There's a vector v again. So b tau sub v, that's that point there. Let's call it C. And if we want to recover b, then we start with C and we apply tau sub minus v. That will get us back to b. Great, so now we have these translations. And so a natural question is, how do we put the reflections and rotations for the grounded isometries that we already have together with these translations? And are there any other isometries that we haven't thought about yet? So here is our main structure theorem for Euclidean isometries. This theorem tells us what all the Euclidean isometries look like. Every Euclidean isometry is either of the form sigma a tau sub v or rho sub a tau sub v for a unique point A on the unit circle and a unique vector v. So there's two types of isometries. There's isometries that are of this form, and there are isometries of this form, and that's all there is. So we do not need any more exotic kinds of things. The translations, the rotations, and the reflections are enough. We can combine them in very simple ways to get every isometry, and pleasantly in a unique kind of way. So there's no isometries that are both of this kind, so it's either of this kind or it's of this kind, and it's of this kind, then there's a unique A and there's a unique V. It's of this kind, there's a unique A, there's a unique V. So in all cases, we know exactly what the parameters or labels for building up isometries is. Okay, so why is this true? It's actually relatively simple. So suppose that alpha is an isometry. We have some isometry of the plane. And suppose that the isometry sends the origin, which is our point O, 0, 0, to another point, let's call it O prime. So there's the origin, and this isometry that we're thinking about takes O to O prime over there. Okay, so define the vector v from O to O prime, that vector. Now consider what happens when you take origin O, you apply alpha, and then you apply tau sub minus v. Okay, so there's the origin. We apply our isometry alpha, twist things around, but the origin is sent up here. And now we're applying tau sub minus v, so we're going exactly backwards from where we are. And so, necessarily, the origin at least goes back to where it started. So this composite alpha followed by tau sub minus v is a grounded isometry because it fixes the origin. And we know all about grounded isometries. We know that either it's a reflection or it's a rotation. corresponding to some point A on the unit circle. In case this thing is a reflection sigma A, then we can rewrite this by multiplying on the right by the isometry tau sub v, which is the inverse of this one. So if we apply tau sub v on the right, then crucially that will get rid of that tau sub minus v because they are inverses. And we'll just have alpha equals sigma sub A tau sub v. And similarly in this case, we apply tau sub v on the right again and we get alpha equals rho sub A followed by tau sub v. So in either case, we have very explicitly our isometry written as a product of a reflection and a translation, or a rotation and a translation. And this is elementary, relatively simple, but beautiful characterization of isometries. And it's really the starting point now for an interesting discussion of the geometry and the algebra and the group theory of this full isometry group. So it's quite a rich story now, and we can investigate that, and we'll do that in our next video. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.